Hello, everyone. Welcome to the last but one session of the workshop. So this will be a post-talk and student presentation session. So the first talk will be by Honors Aman, and he'll be talking about online bipartite matching with degree information. He's a postdoctoral fellow at MIT.
Thanks for the introduction. And thanks to the organizers for a nice conference. So it's been very exciting to see these talks. I hope everybody had a good lunch. So today I will be talking about a recent paper called Optimal Online Bipartite Matching with Degree Information that appeared at NeurIPS 22. And it's joint work between me and Justin Chen and Piotr Indyk, you can see here. And this research falls in this line of work of algorithms with predictions that we've already seen several examples of in this workshop. So I'll go over this a little quickly. But as you know, it's motivated by recent developments in machine learning. And the idea is that to assume that your algorithms are equipped with some sort of predictor that can predict some future feature of your input based on past input. And the hope is that if we have like such predictors, we can maybe go beyond the worst case analysis of algorithms. So this has been studied in several areas. So for instance, in streaming, one common predictor is if you have a stream of elements, you can predict the frequencies of the elements. So this has been applied in frequency estimation, distinct elements counting, FP moment estimation, and a similar idea you can also apply in triangle counting and graph streaming. And maybe more relevant to this workshop, which we've seen many examples of, is that this has in particular been studied a lot in connection with online algorithms. So like algorithms like scheduling, caching, ski rental, and for what I will be talking about for this talk, matching or online bipartite matching. So we've seen some of these desirable properties before of the predictors. The consistency, robustness, smoothness, and learnability. And here the consistency means that if somehow our predictor is accurate, predicts what it should predict, then hopefully we can, if for instance for online algorithms, if we consider competitive ratios, maybe we can go beyond the worst case competitive ratios. And there's the robustness that even if the predictor is bad and provides useless information, hopefully if we can design these algorithms in a good way, we will still do at least as good as we would normally do in the worst case. And there's the smoothness property, which is to say that as the quality of the prediction deteriorates, then there should be like a smooth transition between these two regimes. And finally, we want like this predictor to be something that's realistically learnable. So it can't just be anything. And it can, of course, like these predictors can be based on machine learning, but they can also be simpler predictors. So for instance, if you have a sequence of graphs that develop over time, you can maybe use some information for the past graph to predict these features for the future graphs. So in this paper, we focus on the online bipartite maximum matching problem. And just to recap what it is, so in the offline version of this problem, we're given a bipartite graph, and the goal is to find a maximum matching. And this is a problem that can be solved efficiently in polynomial time. So in the online version of this problem, we have a set of offline nodes, and we have a set of online nodes that reveal their edges one at a time to the offline nodes. And once an online node arrives, we can choose to match it to some available node in its neighborhood. So for instance, we could match to the top node here. So this is like a kind of a game where we have incomplete information, and it should be clear that we cannot do as good as in the offline setting. So for instance, here we had no way of knowing that we shouldn't match this on offline node. So when the next node arrives, we can't match it. So in this example, I guess you end up with a matching of size 4. And as we've seen, as you know, the way we measure the quality of these online algorithms is often in terms of their competitive ratio. So it's specifically this fraction, for an instance, it's the expected value output by the algorithm divided by the expected value of the optimal solution. And if this is quantitatively C, then we say that the algorithm is C competitive. And you will notice that I have an expectation over the optimal solution, and that this is because we will not consider worst case I, but we will consider distributions or instances I. So there are two very classic algorithms for this problem. The first one is simply greedy. Whenever an online node arrives, we match it greedily to a node any available node in its neighborhood. And this algorithm you can show is half competitive, and you've probably seen the proof before. So the idea is that it's an easy, simple exercise. It produces a maximal matching, and you can show that a maximal matching always has size at least half that of a maximum matching. But it turns out that we can in fact do better. There's this another very simple algorithm called ranking that starts with we pick a uniformly random permutation of the offline nodes, and whenever an online node arrives, we look at its available neighborhood and we match it to the first available node in terms of this permutation. And this was famously proved by Karp and Vasirani that this algorithm attains this 1 - 1 over E competitive ratio, and this is in fact optimal. They have this worst case example, which consists of n offline node and n online nodes. And the first online node is connected to everything. The next online node is connected to a subset of size n - 1, a random subset of size n - 1, the next to a random subset of that of size n - 2, etc. And you can show that the best, this is very symmetric, so basically the best you can do is just match greedily, and if you analyze this, then you get this 1 - 1 over E. So this paper, we ask whether we can somehow improve this using some sort of predictions. And we propose this algorithm that's called min predicted degree. And the predictor we use is a predictor. We use a predictor that predicts the degrees of the offline nodes in the final graph. So for each offline node, we have a prediction of its final degree. And then this minimum predicted degree operates very simply. Whenever an online node arrives, it looks at the available neighborhood and matches to the one of minimum predicted degree. So it's similar to the ranking algorithm, but like this permutation is no longer random, but it's induced by the degree predictions. So this on the left, we could have the degree predictions of the offline nodes. An online node arrives, and in this case, we would match it to the top node because it has the minimum predicted degree. Then this node arrives, can't be matched, and this node arrives, and we would match it to the one that has predicted degree 1. And the intuition should be that if a node has a large degree, it's a very popular node, then it's maybe not so urgent to match it immediately. Then we can postpone it to the future to matches. Whereas like if it has low predicted degree, maybe it's a good idea to match it sooner rather than later. Again, I want to point out that these predictions could be made using some machine learning machinery, but they don't have to. If like we could have a sequence of graphs that develop over time, and we could use the predictions from yesterday's graph to predict the degrees of the current graphs. So let's first ask a question whether MPD is better in the worst case. And this turns out to be a disappointing no. So even if we have exact degree predictions, it only attains a competitive ratio of a half. So here's an example. The nodes V1, V2, and V3, V4, V5, and V6 arrive in this order. And basically V1, V2, and V3 will be matched to the bottom 3 nodes. But as you will see, and then V4 and V5 and V6 can't be matched. But you will see that there's actually a perfect matching in this graph. So this example shows that it's only half competitive. You could also ask, okay, we don't have to use minimum predicted degree. We could do something else with these degree predictions. This may not be the right way to do it. So can we somehow beat 1 - 1 over E in some other way? And the answer is again no. We had this hard example from the KVV paper. And what we can do is we can take root n copies of these on root n nodes. So we basically end up with n nodes in total. And then we add another complete graph, which is like root n by root n. And now we can add edges from this bottom graph to each of the left sides of these bad instances on the top to make sure that all their degrees are the same. And now when we think about it, if we present the algorithm with these bad examples, since all the offline degrees are the same, we gain no help from this degree information. So the answer here is also no. So that's why we turn in this paper to average case analysis of this algorithm. And the model of graphs that we consider is what's called the CLVB random graphs. So basically we have n offline nodes and m online nodes. And we have some weights for each of the offline nodes and some weights for each of the online nodes. And now each edge vi, vj appears with probability exactly pi times qj. And these events are independent. So these could be the weights, and this edge, for instance, will occur with probability of p3 times q1. And this is like a fairly large class of random graphs. For instance, it includes the Erdős-Renoi graphs. So if you set all the QIs to be 1 and set all the PIs to be the same, then each edge is there independently with probability p. Okay, so here's the main theoretical result of the paper. And that is that this algorithm, minimum predicted degree, if we have access to the expected degrees of the offline nodes as predictions, then this is in fact the optimal algorithm to run, in the sense that, in a very strong sense, it's stochastic. Whatever size of matching we output, stochastically dominates that of any other algorithm with output. So this is, in a very strong sense, the best algorithm for these graphs, if you have access to these expected degrees as predictions. So here it is formalized mathematically. If A0 is MPD and A is any other algorithm, then if we draw a random instance CLVB instance for any t, then the probability that A0, which is MPD, is larger than t is larger than the probability that A outputs a value that's larger than t. And I'm going to sketch you a proof of this result. It has a very neat proof, I think. First of all, I want to make it a little easier. You can think of A as being deterministic. Basically, if A is randomized, you can make all the coin tosses in advance, and then you can prove the statement conditional on these coin tosses over the randomness of the instance. You can think of A as a deterministic algorithm. Any questions so far? That's one. I think for these types of graphs, minimum predicted degree is actually, I guess it should be the same, but it may be worth considering, I think. It may or may not be harder to predict, but yeah, it's a natural thing to consider. Okay, so let me sketch you the proof. Let's assume for simplicity that all the QIs are the same. So the probability of being connected to a node VI is just equal to PI. And here's the theorem again. So let me introduce some notation. I'll say that this probability vector P prime dominates P if it holds coordinate-wise that PI is smaller than PI prime. Oh, sorry? I mean, it doesn't matter because all of the all of the neighborhoods of the online nodes are independent and identically distributed. But I see maybe you could fix the randomness in the beginning, and then an adversary could like change the order. Yeah, so yeah, we don't allow that. But yeah. So yeah, P prime dominates P if it coordinate-wise holds that Pi prime is larger than Pi. And actually, we will say that this is true even if we have to permute the coordinates. So the main lemma we need to prove this result is this very clean statement that if P is dominated by P prime, then so it's a statement about MPD. So remember that A naught is the MPD algorithm. Then the output of A naught on IP prime stochastically dominates the output of A naught on IP. And this may be a little surprising. So let me first sketch how you prove this theorem given this lemma. And I'm going to sweep some things under the rug, but just to give you the high level idea. Let's do induction on the number of online nodes. You can check the base case yourself. And let's condition on the neighborhood S of the first arriving online node. It's some such subset of the offline nodes. And we can assume that it's non-empty because if it's empty, then neither of the algorithms can do anything, and then we're down to m-1 nodes, and we can apply induction. So what do these two algorithms do? They pick some offline node, match to it, and then basically we can think of them as removing this node, or removing this entry from this probability vector. And A naught will remove the minimum element of this neighborhood S, but A could remove something else. What's the main observation is that since A naught, min predicted degree, removes the minimal element, we will have that, after the two algorithms run on the first neighborhood, this dominance will hold. So the remaining degree vector for min predicted degree will dominate the one for the other algorithm. Now we can apply the induction hypothesis combined with this lemma. So the probability that A is at least T is the probability that on the reduced instance that A on this reduced instance is at least T minus 1. But now we have M minus 1 remaining online nodes, so now we can apply the induction hypothesis. And secondly, in the next step, we can apply this main lemma on the dominance. So P of A comma S is dominated by P of A naught comma S. And now we can translate this back to the probability that A naught of IP is larger than T, is at least T. So in this proof, I've swept something under the rug because the algorithm A may actually choose not to match anything when it sees this neighborhood, yes. But you'll have to trust me that you can also deal with this. Oh.
Explain why PAS is less than PA naught.
I mean, basically you have this this vector of probabilities P, and A naught, you have some subset of that, and A naught removes the minimal element, and A removes something that may be larger. So you can kind of sorry, it's important that this you may have to permute the PIs for this to hold. So let me give you the sketch of the proof of the main lemma. So the main lemma is this: that if P prime dominates P, then min predicted degree on IP prime dominates that on IP. And it's again on induction on the number of online nodes. And basically the main idea is that you can couple these instances IP and IP prime such that the neighborhoods of the first online node is an IP, and the first online node T of the node in IP prime will be such that S is contained in C, or S is a subset of T. And this should be kind of intuitive because we have this dominance that all the probabilities in IP prime of being matched to each offline node are at least as large as they were in as they are in IP. So one way to do it formally is that you sample the neighborhood of the first node arrives, V1. You sample each node I with probability Pi to get S. Next, you sample each remaining node with probability some number you have to choose appropriately to get T. And using this assumption that Pi prime is larger than P, this sampling actually makes sense. This gives you a set T, and you can check that each element Vi is contained in T with probability exactly Pi prime. Yeah. So let me condition on these two sample set S and T, and let me assume to make it simpler that S is not the empty set, and you'll have to trust me that you can deal with that case as well. So the main observation is that after applying a knot, we assumed to prove the lemma that we had this dominance between the probability vectors. And the main observation is after we apply a knot, or like min predicted degree, this dominance will still hold. And yeah, here we essentially use that. Yeah, you have to you commute some elements to make it hold, but the intuition should be that since T is larger than S, a knot can pick a smaller element, an even smaller element. So now it's easy to finish the proof. So we essentially did the same as we did on the last slide. We look at what's the probability that min predicted degree on IP is at least T. Well, that's the probability that on the reduced instance, where we have this remaining probability vector is at least T minus 1. Now we apply the induction hypothesis, and we translate back to the probability that the A naught on IP prime is at least T. Yeah, and I'm doing this conditioning on S and T. The main point is that since this holds for any choice in S and T, it also holds unconditionally. Yeah, so that's a sketch of the proof. So the next question we could ask is, okay, so we've seen it's on CLVB graphs, it's the optimal algorithm that has the optimal competitive ratio. So what is it? And the embarrassing answer is that we don't know. But it would be nice to figure out. So we've seen that it's in a certain sense with degree information, it's the best algorithm on CLV graphs. But what can we say about the competitive ratio? So we know that symmetric CLVB graphs, which are the CLVB graphs where all the QIs are 1, is a special case of what's called known IID graphs. Known IID graphs, you can think about, you have your offline nodes U, and you have some probability distribution over these over subsets of these offline nodes, and each arriving online node picks a neighborhood according to this distribution. And it's known that in this model, and it's called known IID because the algorithm designer has access to or knows about this distribution. And it's known that in this model you can get a competitive ratio that's larger than 1 minus 1 over E. And since CLVB is symmetric CLVB is a special case for of known IID, and since we know that this is the optimal algorithm, we also get a competitive ratio of at least this number. But it's an open question what exactly is the competitive ratio of MPD on CLVB random graphs. And we have a conjecture, which is basically when all the PIs are the same, the degree oracle doesn't give you any extra information. So yeah, you have to think about it a little bit. There's some reasons to believe that this could in fact be the worst case for the worst case distribution for MPD on CLVB graphs. And in this case, we can analyze MPD exactly. And if you've ever seen an analysis of the Coupon conjecture problem, you basically do the same thing. You can, since everything is symmetric, the time it takes to go from K to K plus 1 matched node doesn't depend on which node you matched. So you can basically, you can run a similar analysis as in the Coupon collector problem, where you look at the expected times to go from K to K plus 1 nodes, and you want all of these expected times to sum up to N. So if we just consider the simple case where M is equal to N and all PIs, let's say that they're equal to DON, then we can calculate the fraction of matched edges exactly. And in fact, we can also provide some good upper bounds on the size of the maximum matching that are very close to being optimal, using some Hall's marriage theorem. And then we can show that in fact the competitive rate is at least 0.831. But yeah, it would be an interesting problem to prove this, or like figure out what is the competitive ratio of MPD on CLVB random graphs. So let me talk a little bit about robustness to prediction errors. So we know that for certain graph distributions, MPD gets the optimal competitive ratio. So this corresponds maybe to the consistency, but we know that it's greedy, so it always gives at least a half competitive ratio. And we would like some transition between those two. And we have some partial results in this way. So if you consider two degree predictors, sigma and sigma prime, they induce some ordering of the offline nodes. And what we do is basically we run ranking according to this the ranking algorithm, but with this ranking of the nodes. And what we can prove is that if you look at the minimum number of offline nodes that needs to be removed, so that these two degree predictors give the same order of the offline nodes. And then for any graph G, the size of the matching output by MPD on sigma and differs by at most this quantity from the size of the matching when we use sigma prime. So you could think here of sigma as the perfect predictor and sigma prime as some predictor that's where this order has been slightly perturbed. So this gives some idea that if you perturb these degree predictions somewhat, then your algorithm doesn't deteriorate too much, but it's not very strong. For instance, you could consider CLVB random graphs where all the probabilities are close to, say, 1 over n, but they have like some order, and then you could reverse them all, but still have them to be very close to 1 over n. And then this number delta would be n, but you would expect that that MPD behaved the same way on these two, almost the same way. So this is another open question that would be nice to solve if we can get like better robustness guarantees in terms of say L1 and the L1 error of the predictions. And you could consider this for CLVB graphs. You can also consider it for general graphs, but in that case, I think that this lemma may be tight. So in that case, you probably have to modify the algorithm as well. So let's talk a little bit more about some tangible instances on how MPD performs. So we have another result in the paper that basically says that the evolution of these of MPD on these CLVB random graphs, you can model that using a system of differential equations. So if you only have like a finite, like a constant number of different degrees, then you can in fact solve these differential equations and you can figure out exactly what the competitive ratio is. But this is unfeasible in general. But for certain instances, we can actually solve these equations or give good solutions to them. So for instance, if we consider these power law graphs, we can get good lower bounds on the performance of MPD. And it turns out that here MPD performs very favorably. We also run some other experiments where we compare. Here we compare min predicted degree with the actual algorithm min degree, which gets access to the exact minimum degree in the final graph. So this is not an online algorithm. And we also compare it to ranking, and we see that min predicted degree lies quite a bit above ranking. And we also analyze some predictor noise, where instead of getting the exact predicted degrees, we look at some random subset that gets smaller and smaller of the online nodes, and we, instead of getting the degree of a node, the expected degree of a node, we get like the expected degree of a node, or the degree of the node that it will have in this random subset. Okay, and here's some other experiments on. This is on some real world data where this Kyler data set describes some communication networks of internet routers that change over time, and we use the first graph in the sequence of graphs to predict the degrees in future graphs. And as we can see that, we can have a ranking and min predicted degree and min degree. And we can see that min predicted degree, it's the quality of its estimate deteriorates over time. And that's probably because like as this graph develops, the predictions get worse and worse. We compare to some other benchmark algorithms where it also seems that min predicted degrees perform favorably. So any questions so far? Guess we can. I guess I'm almost done. So just to mention that there are some, we also have, we have like a couple of other results in the paper that I didn't get time to talk about, but just in case you're interested, then these might be reasons to look into the paper. So I mentioned this thing that for a general sequence of the degree predictions, we can model the evolution as this Markov chain. I guess it's not so surprising, but but you can do this basically. You have to look at the probability of if you're matching a node of degree d, you have to pick it in the random process, but you can't pick anything that has degree smaller than d. And we have this theorem that the evolution of MPD on these graphs can be cast as the solution to a related set of differential equations. And we also had some. I mentioned that we could use Hall's marriage theorem to overbound the size of the maximum matching in these random CLVB graphs. And I think we also had some nice techniques for this. Basically, we describe a set of offline nodes where with high probability, the neighborhood of S is small. So more specifically, S is the set of nodes of degree 1. And we start with the set of nodes of degree 1, and we look at the neighborhood on the right-hand side, and then we include all nodes that has its full neighborhood in these nodes on the right side. And you can analyze these sizes, and you can use this kind of technique to get good upper bounds on the matching size produced. The maximum matching in these random graphs. So let me finish with some open questions. I guess the most interesting one is what is in fact the competitive ratio of MPD on these CLVB random graphs? That would be nice to resolve this conjecture I mentioned earlier. There's this other question that I discussed, which is whether we can obtain better robustness guarantees in terms of, say, the L1 error or some other metric. And then more generally, it might be interesting to consider. I think it would be interesting to consider other online bipartite matching problems. For instance, you can consider the weighted case. So the weighted case to obtain competitive ratios, you have to make this assumption that you can dispose edges over time. But I think it's interesting to consider what would be some good predictions that would both be realistic and then could maybe help improve your algorithms in this setting. And also, this degree predictor is like, the idea is that it predicts like somehow the importance of the popularity, and this is in a sense also what's used in other papers, like on frequency estimation, where you predict frequencies. So I think it's and I think Sandeep here has used it for some triangle counting in graph streaming. And I think it's interesting to figure out whether these degree predictions could be useful for other graph problems. So yeah, that's basically it. Thanks for listening.
Your algorithm like stochastically beats other algorithms. So it seems like almost when you're comparing to some other benchmark, your competitive ratio is 1. Like
I see.
Like so can you comment on that? Like what if you were to change the benchmark in some way, how would that translate to your results of like stochastic?
Wait, what do you mean that if the benchmark is to achieve the best competitive ratio and you want to get as close to that as possible? Or
It seems like somehow your result is implying a competitive ratio of 1 in some setting, and I'm not sure which one exactly. Is there some way to translate that in like in terms of comparing it to an online, like optimal online algorithm?
yeah, I mean there might be. I'm not sure, but I understand where the sensation is coming from.
Hi. So as you showed at the beginning, the mean prediction is not useful in the worst case.
Right.
Did you think about other possible predictions which would be useful? Of course, you could predict the order in the KVV, and then you could get like one competitive algorithm.
Yeah.
But that's not very learnable.
Yeah, you can predict you have to like stick to some simple predictions that actually make sense to, I guess in like some learnability context. Yeah, I think we had like some other ideas, but I think that most of them are still not better in the worst case. I mean, there's also the question of how you use the predictions, right? So maybe you can actually use min predicted degree. So you can use the predicted degrees to construct some algorithm that somehow interpolates between ranking and using the smallest degree. I don't know if that's possible. Sorry, what did you say? Oh, yeah.
Knowing just the degrees, you proved a 1/2 lower bound, right?
Say again, sorry. I'm not
You
sure.
proved a 1/2 lower bound in the beginning for the competitive ratio.
Did you say root n?
1/2.
1 by root n? Or by 1 by 2?
1/2.
Right. Yeah.
That is for the deterministic case, right?
Yeah, that's.
Do you also have a 1 minus 1 by bound for randomized?
I mean, you can always choose not to use the. Oh, I see. So you're saying if, well, I guess
randomization is allowed in the beginning when you define the model. Do you have any hardness there?
I mean, you can always use when you say the randomized case. What the distribution?
You're allowed randomization in the algorithm.
I see.
Then can you get a competitive ratio better than?
I mean, I feel that there should be like. Oh, I see. So can you say the question one final time? You say.
So in the beginning, you had a construction, right?
Yeah.
You took AVV's construction and added these root and
root n times. Yeah.
Yeah. So that was for the deterministic case to prove a 1/2 bound.
Oh, it also beats the random case if you can use a random algorithm.
Okay.
Yeah. I mean, for this instances, because it's very symmetric, you can argue that like the only thing that like it doesn't matter what you do, you just match greedily. So whether you do that deterministically and random or randomly doesn't matter.
No better upper bound than 1?
I
mean the hardness or the upper bound on the competitive ratio of MPD on CLVB random graphs. Do you have a hardness there?
Do you say empirical CLVB? Or do you say?
No, I'm talking about open question 1. So you don't know the exact competitive ratio, right?
Yeah. I mean, it's not 1. It's a number below 1.
Yeah. So is there any bound on this, or do you know any?
I mean, I guess I can go back to. I guess we have this some number that's very close to 0.831 as an upper bound.
Okay.
Because you can like yeah, for these adders, when we random graph, you can know exactly how MPD performs, and you can also, I think you can even like exactly find the right constant of how of the size of the optimal solution. Yeah, and MPD is the best thing you can do. Yeah, so yeah.
Thanks.
Questions? Let's thank the speaker again.